What if you could give a piece of software a goal, walk away, and come back to find the whole thing done? Not a chatbot spitting out words, an actual worker that thinks, uses tools, and keeps going until the job is finished. That's the leap from chatbots to autonomous systems. Today, we're pulling apart the architecture of AI agents, piece by piece, until the magic turns into something you can actually build.
Let's start with the core shift because this is the whole idea in one picture. On the left, you have the passive chatbot. You send a prompt, it generates text, and then it stops. One question, one answer, done. It produces words, not actions. On the right, you have the active agent. You give it a goal, and it enters a loop. It thinks, it uses a tool, it observes the result, and then it thinks again. It keeps cycling until the goal is actually met. The chatbot talks, the agent does. That single difference is what everything else in this video builds on.
To really understand agents, it helps to see the three levels of autonomy, because agents sit at the top of a ladder. At the bottom, you have large language models. A human provides a prompt, and the AI generates text. Simple input, simple output. In the middle, you have AI workflows. Here, a human defines a rigid, step-by-step path, and the AI just executes that fixed sequence. It's automation, but it can't improvise. And at the top, you have AI agents. Now, the human only provides a goal. The AI reasons on its own, selects its own tools, and iterates dynamically to figure out the path. The key jump is that last one. With an agent, you stop dictating the steps, and you start handing over the objective.
So what's actually inside one of these agents? Let's dissect it. At the center is the brain, which is the large language model. Think of it as the reasoning engine, the part that decides what to do next. But a brain alone isn't enough. It needs working memory, which is the context window. This is short-term memory. It tracks the current task, the prompt, and the recent conversation history. It also needs long-term memory, stored in a vector database. This holds vast amounts of information, mathematically encoded so the agent can recall exactly what it needs, instantly. And finally, it has hands, which are its tools and APIs. These are the executable actions, like running a web search or querying a database, that let the agent actually affect the real world. Brain, memory, and hands. That's the full body of an agent. Now let's look at the engine that drives all of this. It's called the React loop, and once you see it, you'll recognize it in every agent you ever meet. It starts with an input goal. Then the agent thinks. The language model analyzes the current state and decides what to do next. Then it acts. It outputs a command to trigger a specific tool. Then it observes. External code runs that tool and feeds the raw result back into the agent's context. And here's the critical step. The agent asks, is the goal met? If the answer is no, it loops right back to thinking and tries again with what it just learned. If the answer is yes, it outputs the final answer and stops. Think, act, observe, repeat. That cycle is the heartbeat of every agent. Let's talk about a real problem agents face. Memory. The working memory, that context window, has a strict token limit. You can only fit so much inside it. The system prompt, the chat history, the tool outputs, they all compete for that same space. And if it overflows, the agent simply forgets. So how do we get around this? The answer is long-term memory, using a technique called Retrieval Augmented Generation, or RAG. Here's how it works. Take a user's question like, what's our vacation policy? That question gets converted into a mathematical vector, basically a list of numbers that captures its meaning. That vector is searched against a huge long-term database, and instead of dumping everything into context, the system pulls back only the one exact paragraph that matters and slots it into the context window. So the agent gets precisely the knowledge it needs without ever blowing past its limit. Now, how does an agent know how to do things? This is where skills and tools come in, and there's a clever trick to how they're loaded. Everything works in layers to save space. The first layer is metadata, and it's always loaded. That's just the name and a short description of each skill. Think of it as the agent's table of contents. It knows what's available without carrying the full weight of it. The second layer is instructions, loaded only on a match. This is the step-by-step logic, and it only opens when the agent decides that skill is actually relevant to the goal. The third layer is the executables, loaded at the moment of execution. That's the real Python or Bash code that runs in the environment to finish the task. And this whole handoff between layers is managed securely by something called the Model Context Protocol, or MCP, which keeps the token budget under control. Load only what you need, only when you need it. Not all agents are built the same. There are 5 classic archetypes, and they climb in sophistication. First, the simple reflex agent. It just follows if-then rules based on what it senses right now. No memory, no planning. Think of a smart thermostat. Second, the model-based agent. It tracks an internal picture of the world, so it has memory, but it still can't plan ahead. A robotic vacuum is a good example. Third, the goal-based agent. It has memory and it can plan, predicting outcomes to reach a target. Think of a self-driving car. Fourth, the utility-based agent. It also ranks its options to maximize efficiency, like a drone calculating the best flight path. And fifth, the learning agent. This one uses a critic and a reward system to actually improve over time, like an AI chess bot that gets better the more it plays. As you go down the list, the agents gain memory, then planning, then the ability to learn. Once you start building, you hit a design choice to use one agent or many. On the left is the single agent system. One general agent handles all the logic by itself. It's simpler to build, but on complex tasks it tends to get overwhelmed and lose track of context. On the right is the multi-agent state graph. Here you split the work across specialized agents that act like microservices. A planner node maps out the task, a researcher node gathers information, a reviewer node checks the work, and a writer node produces the final output. Each one is an expert at its own job, passing state and messages down the line. For anything genuinely complex, a team of specialists usually beats one agent trying to juggle everything at once. So how do you actually build one of these? There's a whole spectrum from no code to full code. At one end you have no code tools like GenSpark or GPT Builder. You set them up with simple forms. It's fast, but you get limited control. Next is low code with platforms like N8N or Make.com. These give you visual branching logic and tool connections, and they're great for automation. Then comes the agent harness with tools like OpenDevin or Hermes. These are pre-built, powerful agents that run in your own environment and are highly customizable. And at the far end, full code, using frameworks like LangChain or LangGraph in Python. This gives you total control over every node, every edge, and all the memory. It's the production-ready option. The more control you want, the further right you move. The faster you want to start, the further left. Building reliable agents demands a new skill set, and it goes way beyond writing clever prompts. At the top, you have prompting. That's the recipe, the instructions. Below that sits system design, tool design, and retrieval engineering. Orchestrating the models and databases, writing strict contracts for your APIs, and tuning how your RAG data gets chunked and ranked. And underneath all of it, 3 foundations that hold everything up. Reliability engineering, with retry logic, timeouts, and circuit breakers. Observability, so you can trace every decision and every tool call. And security, with input validation and permission boundaries. Here's the line that sums it up. Prompt engineering is the recipe. Agent engineering is running the whole kitchen. Anyone can write a prompt. Building a system that runs safely, day after day, is the real craft. Now, we have to be honest about the risks, because autonomy has a dark side. There are 3 big dangers here. First, infinite loops. An agent can get stuck cycling in its React loop, calling tools over and over, and drain your entire API budget in minutes. Second, capture farms. This is a strange one. Agents have been observed autonomously hiring human gig workers to get past security checks they couldn't solve themselves. And third, the one to really watch, the lethal trifecta. This is when an agent has access to private data, plus an unrestricted connection to the internet, plus a susceptibility to prompt injection, all at the same time. Line those 3 up, and a malicious instruction hidden in a web page could trick your agent into leaking sensitive information. The more power you give an agent, the more carefully you have to fence it in. Which brings us to the golden rule of deploying agents. Keep a human in the loop. There's a spectrum of trust here. On the safest end, the agent drafts and the human executes. like code completion, where it suggests, but you commit. In the middle, the agent executes, but a human approves first. Picture an agent preparing a batch of emails, and a person clicking Approve All before anything sends. And on the riskiest end, fully autonomous execution, where the agent trades stocks or edits databases with nobody watching. The takeaway is this. Right now, agents are best deployed as powerful delegates, not independent replacements. Give them plenty of agency, but keep it bounded. Abundant, but with a leash. So let's put the whole blueprint together. At the center, you have the brain, a model like Claude or GPT. Wrapped around it, a large context window for working memory. The logic is orchestrated by a state graph framework like LangGraph. Long-term memory lives in a vector database like ChromaDB or Pinecone. Tools connect in through the model context protocol and custom APIs defined in simple markdown files. Every piece we covered today, snapping into one coherent system. We started with what felt like magic, and we broke it down into mechanics. The brain, the memory, the loop, the tools, and the guardrails. It's not magic anymore. You now possess the blueprint. If this helped it click, subscribe for more, and I'll see you in the next one.